Hello, this is my Physics 2211 Constant Velocity Lab report. To begin with, I will go over the physics principles used in the experiment. The first principle used is Newton's second law, which states that the net force acting on an object is equal to change in momentum per change of time. This means that if the net force is zero, the momentum, which is equal to mass times velocity, must be constant. Additionally, if mass is constant, then velocity must be constant as well. This means that the final velocity is equal to the initial velocity and equal to the average velocity. The second principle used is the position update formula, which states that the final position is equal to the initial position plus the average velocity times delta time. This is the diagram of the experiment I carried out. On the left, a marker is originally stationary on top of a table, and I push it to apply a force to accelerate the marker so it gains speed. The other forces acting on the marker are the weight and the normal force. Since these two forces cancel out as there is no vertical acceleration, the net force is the force I apply to the marker when pushing it, assuming there are no additional forces acting on the marker. On the right, we see the marker after the initial push. Here, the marker is moving towards the right. Behind the marker is a meter-long ruler used to measure the marker's position. We assume that there is no air resistance, no friction, and that the only two forces acting on the marker are the weight and the normal force, which cancel out. So the net force is supposedly zero, which means the marker is moving with constant velocity. The purpose of this lab is to measure the motion of an object moving with a supposedly constant velocity and to compare this observed motion with the predicted motion from a computational model that simulates an object moving with constant velocity. As we will see in the results, the observed motion and the predicted motion are not equal. This video is the observed motion of the rolling marker. I then used Tracker to measure the position of the marker during each frame. This is the analysis of the observed motion. The time in the start of the first frame is 0 seconds. The initial position is the vector 12.82, 0 centimeters. I decided to set the origin at the beginning of the ruler and the positive x direction is towards the end of the ruler. After one frame, approximately 0.0317 seconds have passed, and the new position is 19.10, 00 centimeters. The time difference during the start of these frames is the final time minus the initial time, which is 0.0317 seconds. The change in position is 6.28, 00 centimeters. The average velocity during this first frame is change in position divided by change in time, which is approximately 198, 00 centimeters per second. This section explains how I programmed the initial conditions and the update formulas in the computational model. From the analysis of the observed motion, the initial time was 0 seconds and the time difference between frames is 19 divided by 600 seconds. In the code, this was programmed by setting the variable t, which tracks the time, to 0, and by setting delta t, which is how much to advance the time by after each frame, to 19 over 600 seconds. The initial position and the initial velocity were programmed into the code by setting the ball's initial position to the vector 12.8, 00 centimeters, and the ball's initial velocity to the vector 198, 00 centimeters per second. The velocity update formula does not have to be implemented because I assumed that the net force is zero, which means that velocity is constant and thus we can always use the initial velocity as the current velocity. The position update formula is implemented by setting the ball's position to its current position plus its velocity times the delta t variable from before. This is my implementation of the calculation loop, which updates the position of the simulated ball each time. The first line indicates that the loop will only run while the time t is less than or equal to 0.38 seconds, since this is the length of the original video. The first three lines set the speed of the program and print and graph the ball's position. Then the ball's position is updated using the ball's position update formula from before. Finally, we advance the time by delta t, simulating a frame of the video. The graph is a time versus position graph where the pink dots are the predicted position from the computational model and the yellow dots are the measured position using Tracker. The x-axis is the time measured in seconds and the y-axis is position measured in centimeters. As we can see, in the beginning the dots overlap, which means that the observed and predicted position are the same. After some time, however, the observed position falls behind the predicted position. This difference becomes larger as more time passes. This means that the marker speed is actually changing, which can be seen by the slight downwards curve formed by the yellow dots. In turn, this implies that a non-zero net force is acting on the marker towards the left, which is slowing it down. Some sources of error include camera perspective errors. Measurements that were not directly in front of the camera are slightly inaccurate due to perspective. Another source of error could be inaccuracies marking the marker's position in Tracker and that the only movement in the x direction was considered. The first additional question is, what if the axis flipped? In this case, where the x-axis flipped, the position of the marker would become more negative over time because the right would be towards negative x, and the graph would show a negative slope. Velocity in the x direction would also be negative. However, the magnitude of the position and velocity would still be the same as before. If the y-axis flipped, then there would be no change because only the motion in the x position was accounted for. The second question is, what does it mean? Is it possible for you to say how many pushes and pulls, that is, how many forces, are added together to give zero net force in the case that you observed? The short answer is that it is impossible to know every force acting on the marker. We know that the weight and the normal force are acting on the marker, but these two forces cancel out as there is no vertical acceleration. However, as can be seen on the graph, there is a slight net force towards the left, which is likely due to friction and air resistance. It is also likely that there are multiple other small forces acting on the marker.